let's work on example 22. Going forward with our examples. And so it's going to be, I give you a Markov chain, and we figure out what the invariant distribution is. So invariant distribution for a certain Markov chain, which is going to be a random walk on a graph. Invariant distribution for a random walk on a graph. Random walk on a graph. Specifically, so what are we taking? We're taking a graph with 4 vertices, A, B, C, D. A, B, C, and D. And we have a few edges, which are A to B, A to C. Supposed to draw straight lines, but I'm not doing it well enough. That's fine. B to C and A to D. Now let's make that one not straight. There you go. So we know this represents a Markov chain. You know, if I'm at B, if I'm at B, I might go towards A or towards C. There's 2 choices, so each have probability half. If I'm at A, there's 3 choices and can go to B or C or D. And so that has probability 1/3. So in general, not in general, let's write down our matrix. So we just said it. If I'm at A, it's 1/3 to go everywhere. And I can already see I fell into the usual trap of not making the matrix big enough on the number of rows. If I am at B, we already said it. It's half for A and half for C. If I'm at C, we can see it's half for A and half for B. And if I'm at D, has to be A. Always have to go back. So that's our matrix. Remember, if you like the extra help, feel free to put your labels behind the rows and the columns. Completely fine. So we want to find an invariant distribution. And as I said, so if pi is an invariant distribution, then we have pi equals pi times the matrix P. And we underline pi to really say this is a vector. And P is the matrix here. I didn't write it, but I'm sure you all guessed it. And the way to solve it is you really write what this matrix equation means. And it means 4 linear equations based on the columns of these things. So for example, pi A is going to be equal to half of pi B plus half of pi C plus pi D times 1 if you want. That's a D. Okay, and the reason for this really comes from this column, 0, half, half, 1. And 0 goes for A, half goes for B, half goes for C, and 1 goes for D. And so we have all of these like that. And keep writing your equations. You can see I'm going to run out of space. But pi B is 1/3 of pi A plus half of pi B, pi C. Let's just write them on the side. Pi C is 1/3 of pi A plus half of pi B, and pi D is 1/3 of pi A. So that's the 4 equilibrium equations, and we can solve these. It's not too bad, so let's go. What's the simplest way? What I like doing, as you will see, is really show that the answers are linear. So first thing is, pi A is 3 pi D. Obviously, it came from here. I just switch it a bit. That's a D. My D's are pretty bad on this app, aren't they? Unlike most of my other letters, which are perfect. I know. Jokes aside, so we have that. Then I can take, you can see I haven't quite rehearsed this. That's okay. From this equation, let's remove all the pi A's then, because this way we're going to remove some thirds. So pi B is pi D plus half pi C. And let's just replace that in this equation. So we're going to get pi c is pi d plus half of pi b. So I'm going to put half of this. So half of pi d plus a quarter of pi c. And that's good because then I get 3/4 of pi c equals 3/2 of pi d. Hence, pi c is 2 times pi d. And let's box the equations which really matter. The equations which really are basically answers. So that's one. That's another. My lines are really not working today. That's all right. And so I have these two. I can now replace pi c by 2 pi d in that. And we're going to get pi b is 1/3 of pi a. That's a pi d. And 1/2 of pi c, which is also a pi d. So we're also going to get pi b equals pi d plus pi d equals 2 pi d. And now, having done that, I'm actually very happy because I have a one-dimensional vector space. What I like doing is writing pi d equals a. We have the whole vector pi is equal to, so 3a, 2a, 2a, a. But we know that the values have to add up to 1, right? So these are pi a, pi b, pi a, pi b, pi c, pi d. They have to add up to 1 because they are probability distribution. So the values have to add up to 1. Which means, how many a's do I have? I have 8a equals 1. So a equals 1/8. So I end up with, if I want, I can write my answers fully. I end up with pi a equals 3/8. Pi b is the same as pi c is 2/8. That's 1/4. And pi d is 1/8. That's my invariant distribution for this Markov chain. Will the lines work this time? Yes. Look at that. Not this one. I guess they work after a certain length. And there you go. So this is how you compute an invariant distribution. You get your system, you solve it the way you like. Gaussian elimination always works, but as you can see, in this case, it was a bit simpler. It was a decent bit simpler because this equation, which had lots of zeros in it, said that pi a was directly 3 pi d, and then I can just substitute a few things to get this and that. Notice I never use this equation. That makes sense. In practice, there's always one equation that you don't have to use because the system, has rank which is missing a dimension. And before we end this example, I want to mention symmetry a bit. And if we look at the picture again, B and C have full symmetry. Like if I swapped B into C, like if I did that basically, if I put C here and D here, B here, I would get the same matrix, right? Which means they have fully symmetric roles, which means we expect, at least if we know that there's a unique invariant distribution, we expect pi b to be equal to pi c. Now, we didn't actually know that there would be a unique one. That's fair. But we're going to learn pretty soon that, in fact, we can predict that there's a unique invariant distribution. And so keep that in mind. You can use it. You never have to. But we even kind of saw in the computations that pi b should really be equal to pi c because the equations were almost the same. So you can say pi b equals pi c by symmetry. If you want at the start. And there you go. This is how you compute an invariant distribution.